It's graduation day, and you're a photon, fresh-faced and ready to start off in the world. Your parents were an electron and a tungsten atom, who were brought together by love, fate, and high voltage differential between the cathode and anode of an X-ray tube. Your electron father had quite a journey to get you here, traveling through miles of copper wire until he was boiled off a tungsten filament and accelerated to half the speed of light into a rotating anode where he met your mother. You've got some big shoes to fill. But have no fear, you and your brothers were brought into this earth for a very important task, and that is to be shot through a human in order to produce a diagnostic image. What exactly awaits you when you reach your target? What sorts of interactions will you expect? Will you make friends or pass through town as a lone ranger, meeting only with the phosphors beyond? Well, that all depends. Here are a few of the possibilities that linger on the horizon for a young photon such as yourself. Let's take a tour. Our first stop is Classical College. Here, you will major in classical interaction, also known as Thomson scattering or coherent scattering. This interaction occurs to photons with energies of less than 10 keV, so don't expect an invitation to many frat parties. Here, the incident photon comes into contact with the atom, interacting with an electron somewhere in its orbital shells. The photon doesn't carry enough energy to ionize the atom. The electron simply borrows the energy from the photon and becomes excited. With that extra energy, the electron is not ejected but simply jumps to a higher orbital shell. But because the nature of physics and the least action principle, this electron won't stay there. Nature tends to seek lower energy states, so after this electron's brief time in the sun, the excited electron returns to its humble lower energy orbital. But because of the law of conservation of energy, the incident photon is released from the atom in a different direction and with an equivalent amount of energy. It is then referred to as a scatter photon. The process repeats when that photon meets another atom, and so on. Next, we'll visit Compton University. Here, you can major in Compton scattering. This interaction typically occurs when the photon has an energy in the range of 20 to 40 keV. Just as with Thomson scattering, the incident photon will interact with an electron in orbit around the nucleus of an atom, somewhere in a middle or outer shell. But instead of just causing it to jump orbitals, they meet with enough energy to remove the electron completely, sending it wayward on a journey of its own. That electron is now known as a Compton electron. It will have its own interactions with surrounding atoms based on its kinetic energy and the types of atoms it comes into contact with. When the electron leaves its orbital, thus ionizing the atom it left, the atom feels somehow incomplete, and will fill its incomplete orbitals with electrons from the surrounding orbital shells. As we learned from the Thomson scattering, when an electron drops orbitals, it releases energy in the form of a photon. If the electron was removed from an orbital other than the outermost one, this process will repeat until all lower energy orbitals are filled, in a cascade event that will produce several photons of varying energies. The best news about Compton scatter is that the incident photon, that's you, generally isn't completely absorbed. It will lose some energy, but may have enough energy left over to go and ionize or classically interact with other nearby atoms. Our last stop, Photoelectric University. This university requires you to be a high-energy photon somewhere in the range of 20 to 120 keV. Here, you would experience what we call photoelectric interaction. Photoelectric is another ionizing interaction, but instead of removing a middle or outer shell electron, the incident photon, again that's you, ejects an inner shell electron, setting off a cascade event similar to what occurs in Compton scatter, producing secondary photons. You don't want to be friends with these secondary photons, though, as they usually don't have much energy and never see the light of day. This all may sound grand, but in order to impart enough energy to remove an inner shell electron, the incident photon is usually completely absorbed, ending its short but glorious time in the physical plane. You'll be lucky to experience a photoelectric interaction, as it becomes less and less likely the more energetic you are. In fact, the probability of this occurring is inversely proportional to the cube of the energy you hold, but it's directly proportional to the cube of the atomic number of the atoms you'll encounter. So, here's hoping you meet yourself a nice calcium atom in a bone somewhere. And now remember, no matter what you end up doing once you leave the cozy confines of this X-ray tube, it will be important. Now, good luck and bon voyage.